Okay. Hello and welcome everyone. I'm Jack Freestone, and I'm presenting my talk titled Games of Chance for Peptide Identification. So for those that don't know me, I'm a third-year PhD student here at School of Maths and Stats, and my research area is in using statistical methods for the identification of peptides in a biological sample. And given that this is a sums talk, and sums contains the word mathematics, I thought I'd do a bit of maths today. So in particular, I'd like to go over some of the foundational mathematical theory that is used in aid of being able to identify peptides in a sample. So I've broken up the talk into these three sections. The first part is on the theory of Martingales, so that's the mathematical foundation here. So we'll go through a couple of examples and we'll define it, what Martingale is in a very naive sense. So how do I say it? I haven't given the mathematical rigor that typically goes with the definitions and such, because I think doing that would require a long time, so hopefully you can forgive me. The second part, we'll go through the problem of peptide identification. The reason that it's a problem is because as with any natural science, you're going to have some sort of error, and so your ability to 100% accurately detect the peptides in your sample it's not going to happen. So you're going to have to make some sort of concession that your identification is going to be false, and if you do so, then it would be nice to at least bound the number of false identifications in some sense. And so that's where the third part, the resolution, comes in, where we marry up the Martingale theory and show how it can be used to resolve that problem. Okay? So let's start. Martingales are a descriptor of, a rigorous descriptor of what fair games are. And so I thought I'd start off with this fair game. So 2-up is a simple sterling gambling game made legal once per year on Anzac Day. I had at one point thought that this week was going to coincide with Anzac Day, but anyways, you'll have to forgive me for the week difference. The rules are as follows. These aren't the exact rules, so I've fudged a little bit to fit with my argument, so yeah. A person called a spinner, so you're at a club, say, and then there is a person called a spinner who tosses 2 coins at the same time, and they have this paddle to do so. Then before the coins land, there's a crowd around the spinner, and a bettor among the crowd wagers $X that the outcomes are both going to be heads or they're going to be both tails. So if the bettor is correct, say they wagered that it would be both heads, then the spinner would pay the bettor $X for getting it right. But if the outcome is 2 tails, then the bettor is wrong, and the bettor pays the spinner $X. But if the outcome is neither the 2 heads or 2 tails, that is to say 1 head, 1 tail, then the spinner tosses again until eventually we get 2 of the same kind. So what makes this game fair? What is the sort of intuition that warrants fairness in the game? I mean, I certainly feel it in my bones that this game is fair. You might have thoughts of symmetry or the memoriness property, but that can't be everything. Those things are important, but they're not everything, because if I symmetrically say apply a tax to the earnings of the spinner or bettor, then at least from the perspective of the spinner or bettor, they would feel like the game is somewhat unfair, right? So the reason for that is there's some sort of expected disadvantage from game to game. And so that's exactly how we should define a fair game, that such an expected disadvantage, or rather an advantage, is non-existent. So we can say that a player or both players can agree that the game is fair if their expected wealth after the result of the t plus 1th wager remains the same as it was at the t wager. So, for instance, if the bettor had already wagered three games and is prepared to make a wager on the 4th round, if they calculate that their expected wealth after playing the 4th round agrees with how much they've accrued at the 3rd round, then we would say it's fair. So this leads us to the definition of a martingale. So I remind you of, I've glossed over some criteria here. This is the main chunk of the definition that's important. So consider a random process x1, x2, so forth. So each of these xt's are random variables, okay? And then you can think, if you like, more concretely, that xt is the wealth of the beta at time t. Then we can call the random process Martingale if their expected value of xt plus 1, that is to say their wealth at t plus 1, with the information that is available up to time t, is equal to xt. So let's continue with the example of the 2-up game to see what that looks like. Consider the beta at time t with wealth capital xt, who then wishes to wager x dollars that the outcome in the next round will be 2 heads. So to check that it's a Martingale, we need to find its expected value of the wealth at t plus 1 and show that coincides with xt, right? So there's 2 components here. There's the initial wealth at t, and then there's this additional expected wealth that we can calculate as well. So the wealth at t is known to us, so I've kind of given it this blue color, and then this additional expected wealth is what we have to calculate, because that is unknown to us at time t. So I'm implicitly assuming that the information that is accrued over time is exactly the process itself, okay? So that the blue xt we know, so we add that into our calculation, and then we have to calculate the expected additional wealth. So there's a 50% chance by symmetry that our wealth will increase by x, and there's a 50% chance that our wealth will decrease by x, and so we have that 0.5x minus 0.5x term. And then clearly simplifying it, that gives us just simply xt. So you might have something like this in your head, which is perfectly valid. You have this initial wealth of xt, and then the 50% chance it goes up by plus 6, 50% chance it goes down by minus 6, or down by minus 6, down by x, sorry. And then averaging those 2 quantities, it's exactly xt, right? So I just want to clarify that the notation here is really just a notation for the purpose of today's talk. We're trying to calculate the expected value of xt plus 1, but as you can imagine, depending on what information I have, this calculation might change, because some things that are probabilistic might, in some sense, become constant, right? So this math count ft that I have here on the right is really just sort of an index for the information available to us at time t, okay? All right, so let's do a slightly more challenging problem. It's still fine, so hopefully this will be okay. It's the polyomino model, so another very famous Martingale. Well, it leads to a very famous Martingale. It's a protocol for sampling from an urn. So consider you have an urn of 1 blue ball and 1 red ball, and then each time t you do the following sampling protocol. You sample a single ball at random, okay? You replace it, put it back into the urn, and then you additionally add another ball of the same color to the urn, and then you simply just repeat. So this has the opposite flavor of sampling without replacement, okay? So you start off with this urn, which I've represented as this yellow circle, as urns should look like, I guess. 1 red and 1 blue, you select one at random, so in this case I've selected blue. You place it back, and you add 1 more, and then you repeat, right? So I randomly select another one, but because we have this dominance of blue balls, perhaps not too surprising that a blue ball is selected, and we replace it back, and add an additional blue ball. So this is what the process looks like. Is that okay? So we have the following lemma, where I construct a Martingale, and we can sort of go through the proof of that. Let yt be the fraction of blue balls at time t. So I can represent yt as this xt divided by 2 plus t. Xt is the number of blue balls. 2 plus t, if you agree with me, is the total number of balls altogether at time t. Right? We started out with 2 balls, and then each time we do a sampling process, we put back 1 additional ball. So that's t times, so it's a total of 2 plus t times. And assume, so we have to define an information process that evolves over time. Before it was the wealth process itself for the 2-up game. Here, assume I get to look at each time t the number of blue and red balls in the urn, so I get to have a little peek into the urn or into my yellow circle and have a look at what the contents are in there. Of course, when I sample, it still has to be at random. Okay? Then YT is a martingale. So remember that in order to show that a process is a martingale, we need to calculate the expectation at t plus 1, given everything we know up to time t, right? So at t, we have this fraction of blue balls being xt on t plus 2, exactly what we said. But because I know at time t the number of blue and red balls in the urn, then I know that the fraction of blue balls is the probability of randomly selecting a blue ball from that, right? So there's a probability of xt on t plus 2 that a blue ball will be sampled, and in that case, what will happen to our fraction? Well, the numerator will iterate by 1 because we've replaced back that blue ball and have added another, so that goes to xt plus 1. And then in a sort of trivial sense, because we're always adding another ball back into the urn, the denominator will go up by 1 to t plus 3. Okay? But what about in the case that a red ball is sampled? Well, that's just 1 minus the probability that a blue ball is sampled. And in that case, what happens to the numerator? Well, the numerator is just simply counting the number of blue balls in the urn, so that remains unchanged. But again, in a trivial sense, the denominator increments by 1 because we've added now an additional red ball to the urn. Okay, so doing the exact expectation, again, I just want to remind you that this is just simply notation. It's very similar to the expectation you would calculate as you ordinarily would know. It's the weighted average of the outcomes, right? So I have my xt plus 1 divided by t plus 3, that fraction in the event that a blue ball is sampled, weighted by the probability that a blue ball is sampled, plus that fraction in the case that a red ball is sampled, weighted and times by the probability that a red ball is sampled, right? If you are okay with me doing the algebra on your behalf, then it results into xt on t plus 2, okay? And that's exactly the fraction that we desire for it to be equal in order to obtain a martingale. So it's martingale. Perhaps it feels a little odd that such a process that's biased towards, when you do the polyurn sampling, it sort of drifts towards a specific type of color and dominates, right? And so it might feel odd that this fraction of blue balls is a martingale. There seems to be this unfairness. But I point out that it really is fair because when we increment, or in the case that we sample a blue ball, and say it's dominated by blue balls in this urn, there's a high probability of selecting a blue ball, but the changes to the fraction are minimal because you add 1 and add 1 to the numerator and denominator. That will increase the fraction, but not nearly as much as if you were just to add 1 in the denominator when a red ball is sampled. And so that sort of plays out averagely in such a way that you end up with exactly xt on t plus 2. Okay? One of the consequences, or the many consequences of Martingales, is they have these very, very cool theorems. So I would like to introduce one theorem because it will be useful when we get to peptides. And it requires us to go through a definition called a stopping time. So we call tau this random variable, which takes values in set 1, 2, and so forth. So the natural number is minus 0. We call it stopping time if tau takes the value t based entirely off the information available to us up to time t. So to give you some examples, in the case of the 2-up game, tau could be, for instance, the first time the bettor wins 3 wagers in a row playing 2-up. So let's check this, right? So if tau were to be arbitrarily, let's say 10, that would mean that at bets 8, 9, and 10, we saw 3 wins in a row, and we can detect this because our wealth process will go up 3 times, and so we can see this happening. But then for all of the bets 1 to 9, we didn't get 3 increases in our wealth process in a row. And remember that wealth process is what is available to us, right? We get to see that over time. And so tau, because I chose 10 arbitrarily, this works for any other number, this is a valid stopping time, okay? If you prefer, maybe the second example might be of more age. So tau could be the first time a blue ball is drawn in the polyurn model. remember we get to see the contents of the urn at each timestamp. And so if tau would be 10 here, then at the 10th time, I would see, compared to the 9th time, that the number of blue balls have been incremented by 1. And that has not happened at any other time from 1 to 9. So blue ball has been, the number of blue balls at t equals 1, to 2, to 3, to 4, up to 9 has been completely static. And then when we get to 10, it's incremented by 1. Okay, so it's gone to 2 balls, 2 blue balls in here. And this is the information available to us at time t, right? And so tau is another stopping time. Essentially, tau can be thought of as a strategy for you to stop the process using only information that is available to you. That's it.
Yeah.
Yeah.
I think I get the idea, but I'm really confused by the definition. What do you mean takes the value t for all t? So tau takes the value, it's a random variable at each time process. So
Yeah.
it has to take the value 1, and then 2, and then 3, and then up until when do you...
No, sorry, that's the image, the codomain tau. Sorry, so 1 to up to infinity, that's the codomain of tau. So tau has some underlying sample space, omega, into...
But why would it have to match up on to the time t for all t? Because t itself is 1, 2, 3, 4, 5, whatever, right?
T itself, yeah, so I just showed that tau equals 10. That is a certain event, right? And under that event, it's, maybe I can say this, it's measurable with respect to the information up to time of 10. And if you can do that with every value, not just 10, so that's for all values of t, then you have
So your definition is just like saying it's well defined, and then I should just use the idea that you...
It's well defined with respect to the process of information, right? And so your information gets bigger and bigger by definition because you get to include what you've learned before in that included information. So, yeah. Is that okay?
Yeah, that makes sense. Thanks.
Yeah, no worries. So we have the following theorem, now that we've defined what stopping time is. If xt, again, I should really clarify, I have not given you the conditions for things to be well defined here in this theorem as well. This is the main consequence, so assume that everything behaves really nicely. So if xt is a martingale, and tau is a stopping time, which is what we just saw before, then the expected value of your process at time tau, right, agrees with the expected value of the x1, the initial sort of value of the process. Or in the case it starts with t equals 0, then it's just the expectation of x0. So let's see what that means in practice. So in the case of the first example, your expected wealth, if you so for the 2-up game, your expected wealth if you stop after you win 3 wagers in a row is exactly the same as your initial wealth. And in some sense that kind of makes sense because for fair games, if it was to be truly fair, it would be quite odd that I could sort of, in expectation, have some hidden advantage that uses the information available to us from historical events, right? It would seem quite odd. I would say that that's no longer fair. I'm either at an advantage and therefore it's unfair, or unfair in a good way, or I'm at a disadvantage and it's unfair in a bad way. And so it's no surprise that the expectation of x tau, I hope, coincides with your initial wealth. And number 2, the expected fraction of blue balls after you stop when a blue ball is drawn is the same as the initial fraction of blue balls to begin with, and that was exactly 1/2. Is that okay? So we'll use that later on. I ask you now to sort of put aside the Martingale Theory that we just went through, and we'll retrieve it later on at the end. I'd like to go through the final example, which is the problem of peptide identification. So we've gone through 2 examples, and they've been sort of organized in easy and medium, and this last one is slightly more harder. As I said before, there's a problem with peptide identification because you're going to make some sort of misidentifications inherently due to error. But the main goal for biologists is not to identify peptides, it's to identify proteins. So I'm not a biologist, but from what I understand, proteins are very valuable in identifying the functional analysis, I shouldn't use that word here, the functions of a cell. Okay? And so learning about the proteins that are in your sample can lead to you better understanding those mechanisms. Another reason is that a lot of diseases occur at the protein level. They harbor modifications somewhere along the protein. So the protein is a long chain of amino acids. And if I can learn about what proteins I have in my sample, along with the modifications that are on some of the amino acids, then I might have a better understanding of this disease. So if the main goal is to identify proteins, what's the point of these peptides? Well, the canonical method of identifying proteins is to break them into small pieces, and these small pieces are what are called peptides. So these peptides are small chains of amino acids, and so the problem is first identifying those, and then once I identify my peptides, I can sort of accrue the information of those that I think are present in the sample to then conjecture what proteins I have in my sample. Okay, so this is sort of the picture that that you might see if you do this, I guess. You have your proteins on the left, which are really long, stringy, geometrically difficult things of amino acids. And then it's sort of some digestion process. So it's called an enzymatic digestion. And trypsin is an enzyme that cuts the protein into regular pieces called peptides, right? And so that's the thing on the right. They're much shorter amino acid chains. And so once we have our peptides, we isolate the peptides so that there's not a mixture of different kinds of peptides. Of course, that's also a problem, but we try to do our best. And then we pass them through a mass spectrometer, and this produces a spectrum. So this is my, this is probably so great, my beaker of peptides. I don't know what it is, it's been so long since I took chemistry. I was saying to Christina, it's been since G10 that I did biology. So this is your beaker of peptides, and it gets passed through a mass spectrometer, and out comes a spectrum. And ideally, we could use this spectrum to infer the peptide that generated it. It could be sort of a unique one-to-one, right? And I could go, oh, we have this spectrum, great, we therefore know that this peptide generated it. But the problem is noise. So these gray peaks that I've added are the noisy peaks that aren't indicative of the presence of this peptide, while the green are. And obviously you don't have priority to that information, so there's no way for you to know for sure that this peptide DT, DIL, etc., was indeed the one that generated. So we can't do this perfect identification, so what can we do instead? So I'm going to go now through the procedure that is used to account for this, and then show that Martingales can be used to prove that indeed it controls, in some sense, the number of false identifications. Okay? So each spectrum, sorry, I'm not going to time. Okay. Each spectrum is optimally matched against a target database. So how do I explain this? So a target database is all the peptides that you expect might be a sample. Okay. So I have that sort of in this cylinder. I don't know why cylinders are represented as databases in the biological community. And that's like hundreds and thousands of peptides, right? And then I would like to record the best matching one. So the matching procedure, we know what the theoretical spectrum will be looking like for this peptide, DT, DILL, ILAAFR. And what we can do is we can sort of do if you like, an inner product between the peaks of our experimental spectrum versus the theoretical spectrum. And if a lot of the peaks agree, then there's a score associated to it. And high scores mean there's more association between the theoretical spectrum and the observed spectrum. So I got a score of 3.51. It's the best one out of the target database. Then I repeat the same procedure to a database of complete crap. These are called a deep web database, and all the peptides are not expected to be in the sample because they are purely generated artificially by swapping or randomly shuffling the peptides in the target database. So you can see in this first one, MB, EV, PLAK, it's a random shuffling of the first target database, first peptide in the target database over there. And just say for argument's sake that the best match was to this first decoy peptide with a score of 1.96, okay? So we next compete the two matches, the one from the decoy and one from the target, recording the one with the best score and whether it was a target or a decoy match. Okay? The principal idea of doing that is that suppose my spectrum was, the observed spectrum was junk, right? It had heaps of noise, it was very crap, and it wasn't going to match to the peptide correctly that generated. Then, because we have an a priori in sort of all bets rock as to which peptide it will incorrectly match to, it could equally match to the hundreds of thousands of peptides in the decoy database, like the best one, or it could equally match to one of the hundreds of thousands of peptides in the target database minus one for the actual correct peptide. Yeah.
When you say you put in these decoys, so each peptide has a spectrum in your database. You've got a name for it, and then what the spectrum should be.
The theoretical one that we select.
So when you say you shuffle this, you just change the labels.
I change the amino acids, which doesn't have the same effect as, like, it produces a completely different spectrum that it's not, you can't anticipate.
So spectrum, okay.
So you're not shuffling the spectrum piece or anything like that. You're shuffling the amino acids, and then consequently, this will give you a garbage spectrum.
But there's still like biologically plausible spectra.
In the decoy?
Yeah.
There is. So you can remove the ones where they are coinciding with the ones that are in the target database. But the general premise is that we believe, like, to a very high degree, that almost all the peptides in the decoy database are junk.
Okay.
Yeah. So in rigorous cases, what we do is if a decoy happens to coincide with the target database, target peptide, because the random shuffling might produce one that exists already as a relevant one that is a target, then we delete those peptides from the decoy target to keep things there. Okay. So the essential ingredient here is that roughly 50% of the, there's roughly 50% of decoy peptides, and there's roughly 50% of incorrect target peptides. There is a difference of -1 because of the correct target peptide, but that's negligible when you have hundreds and thousands of peptides. And so the idea is that there's a 50-50 chance that after competition, we're going to select the target one or the decoy one incorrectly, mind you, right? It's an incorrect match. Does that make sense? Is that okay? Okay, so if that's the case, then we can use the decoy matches to allow us to estimate the number of incorrect matches in the target database. If I see 10 decoy matches, that would tell me, roughly speaking, that I expect 10 incorrect target matches among that same pool of the sample I looked at. So I need to now come up with some sort of procedure that allows me to report a list of high-scoring quality matches that I conjecture are present in the sample. And this is the following procedure. So I order the matches according to the score from worst to best. So I originally, maybe I didn't clarify, when you see blue, it's going to refer to a target. When you see red, it's going to be a decoy. And so, say I have 1, 2, 3, 4, 5, 6, 7, is that 8? 8 peptides, and I order them from the worst to the best. So the score of 1.9 is at t equals 1, and the score of 10.1 is at t equals n, which is 80. Now, I'd like to estimate, as I said before, the decoys are allowing us to estimate the number of incorrect target peptides. So I estimate the fraction of incorrect matches, those target peptides, using the decoy matches that are greater than or equal to the index t. So you would then assume that it should be dt on capital TT. It's the number of decoys at t or more divided by the number of targets at t or more. There's this +1 term, and this is going to be an essential ingredient that comes up in the Martingales later. But as an example, so dt is the number of decoy matches at t or higher to the right, and tt is the number of target matches at position t or higher. So to give an example, at position 1, that corresponds to that 1.9 score, there are 2 decoys to the right of that or at that position. And at position 1, there are 6 target matches at the position 1 or to the right of that. Is that okay? Okay. Then the tau being a stopping time, okay, be the first time that this fraction is less than or equal to some threshold alpha. So this threshold alpha is a concession of how many, roughly speaking, number of peptides you're willing to accept as being incorrect. Right? I said that we're going to have to accept some of that. So alpha typically is going to be 1%, 5% canonical values. So when we have tau, evaluating it at tau, Q tau tilde, this estimated fraction, is going to be less than or equal to alpha by definition of work tails, right? So you might have this picture. Oh wait, no, I need to follow the video. So if tau were to be at the third position, the idea is that we'll report all the target matches above or equal to the position at tau. So I've circled using a black stroke all the ones that we would report. Okay? Doing this procedure allows us to say the expected fraction of false matches among our reported list is less than or equal to alpha. Okay? So we're going to prove this. This is our third final example, so we're going to go through the proof of this. Okay, so this is a proof sketch, I guess, because again, I feel like the people who developed this theory would be ashamed of my butchering in terms of like dropping things, but I think it makes it more digestible this way. So the expected number of incorrect IDs to total IDs is that expected fraction that we wish to be bounded by alpha. Okay? So I introduced just the letter, the variable Vt, which is the number of incorrect matches among index T or above. And so just rewriting it from words to the actual, using the notation provided, this is the expected expectation of V tau divided by T tau. T tau is the reported list of peptides that I'm going to say, those target ones from T or above, and V tau is the number of incorrect ones at tau or above. So if it's okay with you, I'm going to introduce this D tau plus 1, numerator denominator, hopefully that's fine. But the important thing to realize is that this is exactly Q tau tilde, that fraction D tau plus 1 on T tau. That is exactly the estimated number of incorrect peptides that we were going to use at tau or higher. And by construction, that's less than or equal to alpha. So now we're left with this expectation that remains, V tau divided by D tau plus 1. And the strategy is, if I can show that this quotient is a martingale, and tau is a valid time, then we know from Duke's optional stopping theorem that evaluating the tau coincides with 1, and a little bit of probability theory allows us to show that that's less than or equal to 1. And we're done, right? Because then that's exactly what I desire. I want this thing on the left-hand side to be less than or equal to alpha. Okay. I have to, if I'm going to discuss how xt is a martingale, I have to give some sort of information gain that evolves over time. Okay, that is going to be the following. Assume at time t, we know the number of incorrect target matches, Vt, the number of decoy matches, Dt, and we always know the position of all the correct target matches, okay? That's the information that we're going to be using, that information process. The goal, as with any of the examples that we did before, was we would like to find the expected value of the process, that being that fraction, at t plus 1, given the information we know at time t. Okay? So I'm going to give you a picture of what it might look like when we know Vt equals 2 and dt equals 1. Now, I've kind of ignored here the situation of correct target matches. The reason for that is that xt is completely unaffected by the correct target matches. So if I quickly go back, this xt only looks at things that are incorrect. The number of incorrect target matches, and then the number of, by construction, incorrect decoy matches plus 1. And so we can sort of throw out the correct matches, because if I were to go over from t to t plus 1 and pass over a correct match, that leaves that unaffected. That doesn't look at any of the correct matches. So we can sort of ignore that, those situations. So everything that you see here is an incorrect match. And so if there are 2 incorrect target matches and 1 decoy match at t or to the right, you have the following configurations. It could be the case that the decoy, that one red one, is at the far end. It could be the case that the decoy match is in the middle. Or it could be the case that the decoy match is at the front. So how do we handle this? Well, each incorrect match, I remind you that regardless of a target or a decoy match, they cut from the same cloth, so to speak, right? I can't distinguish them. That's the whole point of constructing these decoys, that they model exactly the incorrect target matches. And so they're completely exchangeable. All three of these scenarios are equally likely. And so if they're equally likely, then the probability of having this at this value here at time t it being a decoy match is 1/3. And the probability that it's a target match is 2/3. And more generally speaking, if I go to the next slide, we have at position t that the chances that it's going to be an incorrect match is exactly the number of incorrect target matches divided by the total, which is the number of incorrect target matches and the number of decoys. And then for the decoy, it's 1 minus this, which is the number of decoy matches divided by the total. So this is what I was trying to explain before. At time t, it could be a blue, a target match, an incorrect target match with that probability. Or it could be a red, a decoy match with that probability. So if we were going to go from xt to xt plus 1, how will that affect our quotient? Well, if we go from t to t plus 1, remember we're counting everything to the right of t and up, right? So, sorry, the right of t and up. So if we go over that t peptide, we're throwing it out of consideration. So going from xt to xt plus 1, if it turns out that that t matches a target, then we would decrease the number of targets by 1. So this would become vt minus 1 divided by dt plus 1, right? With probability vt divided by vt plus dt. But if we had it as a decoy match, right, then we would decrease the denominator by 1, going to dt divided by dt. And that happens with the probability of dt divided by vt plus dt. Okay? So I have the outcomes. I have the probabilities of those outcomes. We calculate the expectation, right? So again, this is notation. We're just calculating the expectation of the process at t plus 1, this fraction, giving the information to us at t. What that is the evaluating that quotient at t plus 1 when we go over a blue or a target match times the probability of the target match plus that quotient in the case that we have a decoy match times the probability it's going to be a decoy. And resolving this, if you again are okay with me doing the algebra here, this resolves down to vt divided by dt plus 1, which is exactly the xt. And so this shows that it's a Martingale, right? It coincides with the exact fraction that we started with xt. And so the proof continued. I can simply go to this equality now by optional stopping theorem. Tau is the stopping time 1, right? Because tau is the first time that the number of decoys plus 1 divided by all the targets is less than or equal to alpha. And I know the number of decoys that's available to me at time t. I know the number of incorrect targets at time t that's available to me. And I know everything about the correct targets. And so that is sufficient for me to know that I can construct tau as a stopping time, because that uses only that information. So tau is valid as a stopping time, and so we have this equality that is exactly the expectation of v1 plus 1, and I think you're going to have me for this last one, but I've left the last one for an exercise because I thought I wouldn't have enough time. But what I can do for you, if you like, is to say this. You have some number of incorrect matches, decoys and targets, right? Call that m if you like. V1 counts the number of those the number of them across all of them, because it's at the start being here, sorry, that are incorrect targets. So you have m trials, and there's a 50-50 chance that it's going to be an incorrect target or a decoy, right? What distribution is that? Binomial. Okay, binomial. D1 is also binomial, except it considers a success as what V1 considers as a failure. So they are both binomial, such that V1 plus D1 is exactly m. So they're like exactly dependent. So this is just a function, the implication of a function of a binomial distribution. So if you've done stat 101 here in my class and stuff, then this is fine. You can actually do this, it's totally fine. And as it turns out, it's symmetrical. It's just your undergrad probability theory I wrote there. So that's why I cut that, because it wasn't maybe these other things. So to summarize, Martingales are random processes that model fairness. The wealth process in 2-up and the fraction of Lugol's and the polynomial model examples. The stopping process, the stopping theorem says that any strategy for terminating a process that uses the information available to us does not improve or worsen the expected process at t. Martingales can be used to control for the fraction of incorrect peptide identifications in an average set, right? Yeah, Martingales. Okay. Any questions? That's basically it. So.